I'm going to show you a few external resources available, and this one in particular with the concept of slipping or tipping. So in the book here, we have this example of a really tall object with a person pushing on it. And there's two ways that this box can move. It'll either slide across the ground, or it'll stay in equilibrium, it won't move. Or it could tip over. And if it tips over, it's going to tip forward around this front corner up here. We can figure out when that is going to tip based on whether the moment created around this front corner due to the pushing force is greater than the moment created around this front corner from the weight stabilizing it. So if the weight is going to stay over the base of the box, then if the pushing force is heavy enough, it'll slide. And with a low coefficient of friction, that would happen. But if the coefficient of friction of the ground surface is pretty sticky, then when you push this high up, it's going to be more likely to tend to tip than it will to slip. So I'm going to start just taking a quick look at an example like this with a box on a horizontal surface, and I'm going to use Matlab. So here's a Matlab online. I've got a block with friction, and I've defined some input variables. So my input variables up here are the weight, the height of the box, or essentially not necessarily the height of the box, because that doesn't matter as much as the height of the pushing force. So H refers to how high the force is applied. The base is the total overall width of the block and a static coefficient of friction. So if I sum forces in Y, my normal force is equal to my weight. My friction force, the max friction force right before slipping, is the coefficient of friction times the normal force. So how much you would have to push to get it to slip? P slipping, the pushing force of slipping, is equal to that friction force. And then if we assume tipping, the normal force is in that corner down here. We're going to do essentially the sum of moments would be a positive moment from the weight times half the base minus the pushing force times the height. So we can calculate out what that pushing force would have to be as weight times base over 2 divided by h. So if the slipping force is less than the tipping force, then the box is going to slip. If they're exactly the same, then it'll kind of like slide on that corner. It'll slip and tip. Otherwise, it's going to tip. So if the slipping force is less than the tipping force, it'll slide. And if the tipping force is less than the slipping force, then it'll tip. So with a weight of 200 and a static coefficient of friction of 0.3, that means my slipping force is going to be 60. And I can look at different heights. So I can give it a base here of 3 meters and a height of 5 meters and run it. And that actually gives us this kind of sweet spot. That's where both the slipping force and the tipping force are 60 newtons. So that's really specific. That's where it kind of just sort of runs around on its corner. But if I make my base smaller, 2, make it narrower, right? The box will tip with only 40 newtons of force. If I make my coefficient of friction a lot lower, so I put something slippery underneath it, okay, now it slips. Okay, so it's still really narrow, but if I have a really slippery coefficient of friction underneath there, then we can get it to slide with only 20 newtons of force. If it's pretty sticky down there, 0.5, we can have something high. Here we go. But we just have to push it down low. We got to crouch down and push it down here. So if I drop my height of pushing to 3, let's see if that's enough. Still tipping. This might be right at that sweet spot. Yep. With 100, it's not going anywhere unless you give it 100 newtons of force, half the weight. And then it's going to just kind of ride on that corner. If I make it a little bit wider, now it's going to slide with 100 newtons of force. Okay. So we've got some if-else statements down here that allow us to kind of play with some different variables and compare that slipping versus tipping scenario. Okay. An alternate version of this is an object just resting on an inclined plane. So we're not applying a pushing force. The force that's applied is the weight. So the weight is going down, but the normal force is at an angle, friction force is up. And we want to know if this is going to sort of tumble or rotate down the inclined plane or whether it's going to slide. So a similar slip versus tip scenario, but without a pushing force, we're dealing more with a weight force here. And this one, I'll take a look at in OnShape. So similar if my slope is 0, right? I can push here. There's my box. But if I bring my slope up to 10 degrees, I've got the ramp, got the crate, got a coordinate system. Right, and here's my weight force. What I like about using OnShape is it visually lets me see if my weight's applied at the center of my block, where that weight force is going to fall. Right? And these dashed lines are showing the weight projected onto the coordinate system. But here's my weight force. And what's really important about this is when the weight is centered over the base, then it's going to be stable. So this isn't really telling me if it's going to slide or not because I don't know anything about the coefficient of friction, but I can see that moment of impending motion would be when here's my friction force and here's my normal force. Normal force is here, friction force is here. So the ratio between those would be the coefficient of friction. Let's take a look at another version. Take the ramp here and increase this to 20 degrees. Go back to that weight force, and the weight is still over top of the base. So there's no issues here. This is still not going to tip over. It's not going to tumble down the ramp. Okay. Let's go a little extreme. Let's go 45. That does not look stable at all. Okay. So here's the weight force. The weight force is not supported by the base. This is definitely going to take a tumble down the ramp. So just playing around with this, we can kind of get an idea. We're at 20, 45 was too much. Okay, 25 is really close. It's still stable. The weight is still over the base. But if I go to 30, let's see, 30 is too far. So somewhere between 25 and 30 degrees is going to be the angle at which this block would start tipping down that ramp. The friction and the normal force here, it's showing the normal, here's the weight. So let's bring the slope down to 20 degrees again. So here's the weight force coming down. The normal force is, if those are the only forces acting on it, the weight force, the normal force, and the friction force. The normal force is essentially the resolution of the weight into the y-axis, and the friction force is the resolution of the weight into the x-axis. So the coefficient of friction for which this would slip is going to be the ratio between the friction force and the normal force. So just a little bit of a tutorial as to how you can use OnShape and Matlab to help you visualize, but also calculate some of our key situations that we're dealing with friction problems.